Now we'll take a look at a pulley problem. So we have two boxes connected by a cord running over a pulley. These right now are magic pulleys, and they're not going to, they have no moment of inertia that we have to worry about. They're massless. They're very nice. So the coefficient of kinetic friction between box A and the table is 0.20. We're ignoring the mass of the cord and the pulley and any friction in the pulley, which means we can assume that a force applied to one end of the cord will have the same magnitude at the other end. Now it's also a little bit magic because the tension at one end is in one direction and the tension at the other end is in the other direction. We wish to find the acceleration A of the system, which will have the same magnitude, now keep that in mind, is the same magnitude for both boxes, assuming the cord doesn't stretch. As box B moves down, box A moves to the right. So that's our setup. It's because I have two mice, one that's connected to the pen and one that's on the computer, so that's why it goes back and forth like that.
Gravitational force on box B is going to be greater than the static friction of box A on the table?
We will assume that because they don't give us the static friction on the table. Since they don't give us the static friction on the table, we have to assume that if it must be moving. Because didn't they only give us a kinetic friction?
We could assume that it's not enough and just save us all some time.
Well, we could.
Think, well, it's not moving, so.
Well, if we know the kinetic friction, can we work backwards to find the static friction?
No.
That's a shame.
No, because the static friction is determined experimentally.
It's not proportional?
No. No. Okay, so we actually have two objects here. Since we have two objects, we have to draw two separate free body diagrams. So let's start with the 5.0 kilogram. And it's important when we use masses here that we pay attention to which mass we're talking about because M is not the same for both of them. A is the same for both of them, but only in magnitude, not in direction. So what forces, let's do, this is box B, this is box A. What forces are acting on box B?
Gravity.
We have gravity down, ooh, that's nice. Gravity down, and yeah, and we call that tension, which is usually FT, but sometimes I forget and just write T. So we have those. Are those two forces necessarily equal?
No.
No, because we are accelerating downward. So they're not equal.
So gravity has to be bigger.
So gravity has to be bigger. So what are the forces acting on box A?
You have gravity down and then the normal force up.
Now, is this FG the same as this FG?
No.
No, different FGs. Call that FGA and FGB. Okay, and I have the normal force up. In this instance, will the normal force up equal the gravity down?
Yeah.
Yeah, because there's no other vertical forces in here. Okay, what else do I have?
You have the tension.
I have the tension. Now, is this FT the same as this FT? Yeah, they are the same in magnitude. Notice they're not actually the same vector because this one's up and this one's to the right. But they are the same magnitude. Well, yeah, we have a magic pulley. Okay, and what else do we have?
Then we have friction going the other way.
And we have friction going the other way. Okay, now I'm going to make a suggestion here. I said you can always define whatever direction you want to be positive. I am going to say for box B, let's define down to be positive, and for box A, let's define the right to be positive. Because if we do that, then our accelerations not only have the same magnitude, they actually...
be in the same positive direction.
Yeah, they'll both be in the same positive direction, so we don't have to like worry about changing the signs. So for box B, I'm going to call down positive. So my net force for box B, I don't have to worry about horizontal because there is none. So my net force for box B is going to be FGB minus FT. Net force is always MA. Now I'm going to say MBA because our mass of box B is different than our mass of box A. Now our acceleration is the same, so I can use the same A for both the same A acceleration for both boxes. That equals the force of gravity on B. B is 2 kilograms, so that'll be 2.0 times 9.8 minus the tension. And so let's see, so this is 2A equals 19.6 minus the tension. Okay, so we have one equation and one unknown, two unknowns. So now let's go over and look at box A. So let's first, for box A, look at our horizontal or vertical. Let's look at our vertical. Vertical is nicer. Okay, so for vertical, it doesn't matter here what we define to be plus or minus, positive or negative, because they're going to be equal to each other, as we mentioned earlier. Since we already determined that they're equal, we can kind of skip the step that says, you know, one's positive, one's negative, you add them together, you get 0, you solve for them. We already know that Fn is going to have the same magnitude as the force of gravity. It's going to be mBg, or 5.0 times 9.8. Let's see, 40, carry the 4, 45, 49. Okay. Oh, yes, that's MA. Thank you. Thank you, that's MA. So the normal force is 49.0 newtons. So now we can look at our horizontal. And we said we would define the right to be positive. So we have Ft to the right, which we don't know. We have to the left, we have minus Fk, because it's to the left, which equals minus mu k times the normal force, which equals negative 0.2 times 49, which equals, let's see, so 49 divided by, wait, wouldn't that just be, no, yeah, 9.8? Yeah, which equals negative 9.8. Okay, so that equals, so our net force is Ft minus 9.8, which is our mass for box A times our acceleration, equals Ft minus 9.8, or 5 times our acceleration equals Ft minus 9.8. Okay, so now I have two equations. So I've got this equation and I've got this equation. So I've got simultaneous equations. 5a equals negative 9.8 plus Ft. Those cancel. 7a equals 19.6 minus 9.8, which again is 9.8. Yeah? Okay, so 9.8 divided by 7, there's one I can't do in my head. 1.4. So A equals 1.4 meters per second squared. What are we looking for? We wish to find the acceleration A for the system. Yay, we did it! Could we find the tension in the cord if we wanted to?
Yes.
We could. Does anyone want to?
Yes.
Oh, okay. All right.
What that box is going through.
Okay, you want to know what the box is going through. Which equation would you like to use?
The one with the 2a.
Yeah.
The one with the 2 in it.
2 is much more.
So 2 times 1.4 equals 19.6 minus ft, or ft equals 19.6 minus 2.8, or ft equals, let's see, it's 16.8 newtons?
Yes.
Yeah.
Okay,
16.7.
16.7. 7?
I think because it's 16.7.
Oh, just from rounding earlier or something?
I don't know.
I think 16 minus 8 is 8.
Okay.
Yep. Okay, so that's the tension on block
10 over 7?
B.
Or is it 10 over 7?
Yes.
And is it also the tension on block A?
Yes.
Yeah.
At that magic pulley.
Magic pulley.